Hello all, my name is Moein Khazraee and I'm a graduate student at UC San Diego. US visa restrictions prevented me from attending the conference and I apologize that I'm unable to present in person. Today my talk is entitled Moonwalk NRE Optimization in ASIC Clouds or Accelerators Will Use Old Silicon. My collaborators at UC San Diego include Zhang and Vega and my advisor is Michael Taylor. We've seen two trends in computation in 2017. The first is the bifurcation of computation into client and cloud. The second trend is the end of Dennard scaling for CMOS transistors, which has led to the phenomena of dark silicon. Compute devices today are limited by power density rather than by transistor density, so we need to use dark silicon-aware design techniques such as specialization, i.e. accelerators, as well as low voltage or even near threshold operation. In this talk, we focus on the combination of data centers, specialization, and low voltage. We've already seen early signs of specialization in data centers. Intel customizes the Xeon processors for large customers. For example, Oracle uses workload specialized SKUs, and Xeon D was apparently created for Facebook. We also see GPUs in the data center. For example, Baidu is using GPU clouds for deep neural networks. We also see FPGA clouds, for example, Microsoft's Catapult project and the recently deployed Amazon EC2 instances. So it's natural to ask, how about ASIC-based clouds? As the cloud client module scales, we are seeing the emergence of planet-scale computations. For example, Facebook runs face recognition on 2 billion pictures per day. Siri recognizes voice for about 1 billion iOS users. YouTube transcodes users' video to their internal Google VP9 format, reaching 500 hours of upload every minute. These enormous computations incur very high costs for the providers, known as the total cost of ownership or TCO in the data center world. These computations share a common property. They are all scale-out computations, meaning that the same computation is being done many times on behalf of millions or billions of users. As these computations become sufficiently large, it makes economic sense to specialize the hardware for that particular computation. This would improve performance and energy efficiency substantially and reduce TCO. But you might say, what about costs for developing ASICs? This cost is called non-recurring engineering cost, or NRE, which could be on the order of millions of dollars. Managing NRE is a key factor for making ASIC clouds feasible. Our paper makes a key contribution by showing how to calculate and optimize NRE cost and when TCO savings would pay off the NRE. So what is the architecture for an ASIC cloud? We've created an abstract architecture for ASIC cloud that can be used for any application. In an ASIC cloud, we want to replicate a hardware accelerator. So first we consider an accelerator, which could be a custom widget implemented in Verilog or a commercial IP. Then we replicate it on a single ASIC die, which we called each accelerator a replicate compute accelerator or RCA. Then we need a control processor to receive the computation jobs and distribute them among the RCAs. Next, there is a simple on-chip network among the controller and RCAs according to the RCA needs. We also need the on-PCB router to route the traffic from PCB to the controller. Finally, if the RCA require external memory, we have a DRAM controller. After establishing the architecture, then we bake it into an ASIC, adding the clock tree, power grid, PLL, packaging, and so on. Now we want a server full of such chips. Consider an array of ASICs. First, there is an on-PCB network among them via PCB traces. Then there is a controller which is connected to the network inside the data center to receive job queries. This controller is used to distribute jobs to the ASICs. We consider an FPGA controller to be consistent among our ASIC clouds, but it could, for example, be replaced by a PCIe-connected Xeon processor. Additionally, non-acceleratable tightly coupled parts of the workload can be done by this controller. Finally, we bake it to a server, considering power delivery units such as PSU and DC-DC voltage converters, as well as chassis, fan, and cooling system. Now we have a server with many ASICs and each of them has many RCAs. Now we can describe the high-level architecture of an ASIC cloud. Considering the servers in the previous slide, there would be racks full of these servers and then data centers full of these racks. In this paper, we consider 1U servers and standard 42U racks. These racks could also contain Xeon servers that do non-acceleratable computation or TCP offload and then delegate the compute-intensive portions to the ASIC servers. To elaborate ASIC clouds, we selected 4 cloud applications as our benchmarks. First, we selected Bitcoin and Litecoin. These are cryptocurrency workloads and are some of the earliest developed ASIC clouds. This was used to calibrate our final results and also close the gap between academia and industry in these fields. We examined also video transcoding, a major workload at YouTube, and modeled it with the H.265 transcoder. Finally, to address the face and voice recognition, we scaled up the Dadionao accelerator into an ASIC cloud for deep learning. We selected these applications for our target ASIC cloud because they have very different requirements, such as being logic or SRAM dominated, requiring high DRAM or I/O bandwidth, or being latency sensitive. So we show a real effort here to properly explore the application space. So what are the key metrics for ASIC clouds? The 2 main metrics for accelerators are energy efficiency, energy per op, and performance, which is dollars per op per second. We want to minimize both of them, but as is often the case, there is a Pareto trade-off. So the conventional trivial weighing is to multiply them together, as with the energy delay and energy delay squared metrics. For data centers, we have a better metric, which is total cost of ownership, or TCO. It not only covers marginal costs of servers and electricity costs, but also includes land costs, labor costs for maintaining the data center, and much more. This metric is indeed much more realistic for ASIC clouds, and finds the one best point in the Pareto space of the 2 accelerator metrics. We use Barroso et al. Data center analysis, who is VP of Engineering at Google. To be conservative, we assume only 1.5 years lifespan for the ASIC clouds. We want to jointly specialize server and ASIC to optimize TCO. To achieve this goal, we developed a complete design methodology that gets RCA properties and outputs a TCO-optimized data center. This flow implements thermal optimization, such as number of fins, their width, height of heatsinks, die size, ASIC placement, and much more. The results are verified by ANSYS IcePack, which is a computational fluid dynamics CFD tool. It also implements power supply design and considers geometry and application constraints and filters out the unfeasible designs. For example, number of DRAMs per ASIC affects number of ASICs per lane. Please read the paper for details. By using the flow from the previous slide, we do a brute force design space exploration and plot the corresponding Pareto curves. In this diagram, the x-axis is energy efficiency and y-axis is performance in terms of marginal cost per op per second, which are the 2 main inputs into TCO. We use voltage scaling as a knob between these two. On each curve, operating voltage increases from left to right, improving the performance but decreasing energy efficiency. This diagram is for video transcoding 28nm and 5 ASICs per lane. As you see, we also explore number of DRAMs per ASIC. The diagonal lines are equal TCO lines, and the closer the line to the origin, the lower the TCO. Based on these Pareto curves, we find the TCO optimal ASIC cloud for an application. Using our flow, we found the optimal ASIC cloud design for each application in 28nm technology and compared it with the state-of-the-art alternatives in CPU or GPU domain. As you see, it outperforms the alternatives by orders of magnitude, which means specializing the hardware and server does pay off. But what is the obstacle for these high improvements? As mentioned earlier, the question is when savings in TCO would pay off the NRE cost. To understand this, we came up with 2-for-2 rule, which connects the TCO improvement and NRE. If the baseline TCO is high or the NRE is low, less TCO improvement is required to save money. For example, suppose you are currently spending $10 million to support face recognition at Facebook. If your NRE for the corresponding ASIC cloud is $5 million, you only need 2 times improvement in TCO to break even, which is easily attained by most proposed ASIC accelerators. But if your NRE was 10 million, no amount of speedup would make an accelerator worth it. So in many cases, the feasibility of ASIC clouds can be determined more by how much we can reduce the NRE than what speedup we attain. This is a major shift from the conventional wisdom in architecture research, where we often chose the best process even though it exponentially increases NRE. In other words, low speedup with low NRE can often be better than high speedup at high NRE. In the next set of slides, I'm going to show you how to estimate NRE. Previous to this paper, academic architects have not had a comprehensive way of modeling NRE. So we developed an NRE model which is accessible for academic use and can open up new research opportunities. There are 5 components in NRE: mass cost, IP licensing cost, labor cost, tools cost, and packaging cost. I'll go over each of these in the following slides. Mass cost is dependent on technology node and also the number of metal layers. This figure shows mass cost for 8 key technology nodes using 9 metal layers. If a technology doesn't support 9 metal layers, then we use the max supported layers, for example 5 layers for 250 nanometer. As you see, there is an exponential rise in the mass cost among technology nodes. For example, mass for 16 nanometer node costs $5.8 million, which is 89 times as much as 250 nanometer. Packaging costs are $105,000 for a flip chip BGA. Here you see IP license costs among different technologies for some widely used IPs. The detailed numbers can be found in the paper. As you can see, IP costs increase greatly with Node and even exponentially for PHY IPs, like DRAM controllers and PCIe. Backend labor cost covers the cost of taking an RTL design and pushing it through the tools to get the final polygons, the GGS that is sent to fab. To model this cost, we talked to a company that had designed several hundred ASICs and also examined commercial literature. We found that labor costs are highly correlated with the number of unique gate instances in the final design. Contrary to conventional wisdom, backend costs, independent of gates instances, do not go up that much with Node, with the exception of 16 nanometer, where double patterning greatly increases DRC errors and design complexity and costs almost twice as much. Next is front-end labor costs and tool costs for both backend and front-end. Front-end design time is application dependent, and I'll give some examples in the next slide in terms of how many man-months is required for an application. We use Glassdoor.com salaries for backend and front-end engineering jobs in San Diego for 2016, and also consider the salary overhead of about 65% due to employee benefits, health, and retirement plans. Tool costs also depend on how many licenses for how many months are required. For the front end, we use our own RTL development efforts to estimate design time, and for backend, we calculate it based on total backend labor months and backend labor salary. Here you see the application-dependent NRE parameters. Gate count and front-end times are based on our own actual RTL implementation by graduate students in our lab. These are just some inputs to our methodology, which is general and can be used for any application. There is also system NRE for the system-level code development for interfacing the ASICs with outside world or the rest of the company's cloud deployment. It includes firmware for the server's FPGA controller, FPGA code for job distribution across ASICs, and software modifications to an existing cloud to use ASIC Cloud servers. Finally, there is a PCB design cost that depends on complexity of the work. For example, it's more expensive for designs with external DRAM. Here you see total system NRE among different applications. In this figure, total NRE for each application in each process technology is shown. For deep learning to satisfy SLA requirements, we kept the running frequency constant and we couldn't go further back than 14 nanometer. As stated earlier, mass cost increases exponentially for newer nodes and becomes a major part of NRE. IP licensing cost also increases exponentially for video transcode and deep learning that use commercial IP. It is important not to confuse NRE and marginal cost. Silicon cost and package for each chip are part of the marginal cost. Change from 180 to 130 nanometer is mostly due to change in wafer diameter, but afterwards the wafer cost increases exponentially for the newer nodes. As we've seen in the earlier slides, NRE is highly dependent on process technology. Also going from 250 to 16 nanometer, there is a variety in ASIC properties as you see here. So choice of process technology can be an effective knob for optimizing ASIC clouds considering NRE. Post-standard scaling restricts our ability to use more transistor or faster transistor switching speeds in newer technologies. Supply voltage scaling limitations reduce the improvements in energy efficiency for newer technologies. Because of this, compute density improves approximately with improvements in feature size, while silicon cost is increasing almost at the same rate, so cost efficiency is quite flat. This analysis shows that we get less and less benefits as we go towards more advanced nodes. Here you see the same Pareto curve for video transcode as we change technology nodes. In each node, only the Pareto frontiers are shown. As you see, there is improvement in both energy and cost efficiency going towards each newer node. However, we first see a large jump from CPU to 250 nanometer ASIC, and as we go towards newer nodes, the gaps become smaller and smaller. So the question is, according to the 242 rule, which node is good enough? You can find graphs for other applications as well as their detailed data in the paper. To see the 242 rule in practice, this graph shows NRE on y-axis and TCO improvement on x-axis. As you see, going from 250 to 14 nanometer, there is a significant improvement in TCO with a slight change in NRE, but after that improvements becomes marginal while NRE increases rapidly. So how can we select the optimal node? This graph includes NRE in the TCO number on the y-axis for Bitcoin application. At the bottom, it shows the node that is optimal for each possible pre-accelerated TCO. At the beginning, GPU is optimal since there is no NRE for it, but as the pre-accelerated TCO passes NRE of 250 nanometer ASIC, 250 nanometer ASIC Cloud becomes optimal. Based on TCO improvements and NRE changes among two consecutive nodes, the break-even point is determined. For example, 14 nanometer is optimal for Bitcoin for a range of $400 million to $2 billion. Here, the final results for each application are shown. You see that TCO should be in range of $1 billion to make 16 nanometer ASIC reasonable. Another point that we see is for Litecoin. Newer technologies become optimal in lower TCO points. The reason is it is SRAM intensive and does not suffer from Powerwall that much. Also, we don't see 130 nanometer in video transcode, which is due to support of LPDDR3 in 19 nanometer and high TCO improvement compared to 130 nanometer. So 130 nanometer never becomes optimal. Please see the paper for more detailed analysis. We've seen significantly high TCO improvements by going to ASIC. But what about applications where accelerators offer only modest TCO improvements? Since all of our benchmarks had high speedups, we developed a methodology to examine this case. We came up with tech parity nodes, which is the node at which an ASIC would have the same TCO as the original solution. Using the graph shown here, you can use the tech parity node and the baseline TCO to determine the combined TCO plus NRE optimal node to use. For example, if your baseline has same performance of 250 nanometer ASIC and you were spending $100 million on your data center, 40 nanometer would be the right node to select. For time constraints, please see the paper how to use this graph. In summary, we've shown that ASIC clouds are a promising direction for deploying new kinds of accelerators targeting large chronic workloads. We present a model for computing NRE which was not previously available in academia. We presented a model for modeling TCO across nodes and show that all nodes can have optimal NRE plus TCO. We also showed an end-to-end methodology for selecting NRE plus TCO optimal ASIC clouds across technology nodes. Thank you very much for listening to my talk. I hope you enjoyed it. Please feel free to email me at mkhazraee@ucsc.edu about your questions.